this video, we are going to discuss hypothesis tests for proportions. Specifically, we're going to focus on a test for one proportion. So what are we testing for? Well, a hypothesis test is used to test whether the difference between the assumed value of a parameter and the sample statistic is likely the result of random sampling error, or whether the difference between the two is great enough to have unlikely been the result of random sampling error. All right, so let's unpack this. What does this mean? Well, first of all, we're talking about the difference between two values. One, an assumed parameter, right? Notice here that this is important to note that we are looking at an assumed value. So an assumed value of the parameter and the sample statistic. So the sample statistic comes from data and the assumed value comes from basically old data, a gut feeling, just an idea, something that we want to test. So for example, let us go ahead and look at example 1 here. Which says, use a hypothesis test to test the claim that less than 20% of college graduates smoke. So notice that this claim is relative to a proportion of 20%. So what we're going to do is we're going to let's assume that the population parameter is equal to 20%. And that assumption is what we call a null hypothesis. So our null hypothesis is that the proportion is equal to 0.2 or 20%. Now we need an alternative hypothesis. And this then is what's going to be in our claim for this problem. So we are testing the claim that less than 20% of college graduates smoke. So our null hypothesis then is that P is less than 20%. Okay? Now, what is our sample value? What is our sample statistic? We're working with proportions, so our sample statistic will be a sample proportion P hat. So what is the data we're given? Well, we have a survey that showed among 785 randomly selected subjects who completed 4 years of college. In that sample, 144 of them were found to be smokers and 641 of them were non-smokers. Since we are making a claim about the percentage of college graduates who are smokers, our sample statistic will be the number of smokers in the sample, which we can see here is 144, divided by the total sample size, which is the 785. Now pay attention here. Notice that our sample statistic is 0.183. So we're looking at something close to 18%. That is indeed less than 20%, all right? So why are we doing a test? Because this difference could be due to random sampling error, or it could be so small that random sampling error is unlikely the cause. So what do we mean by that? Well, let's remember what the sampling distribution of the proportion is. All right, the sampling distribution of the proportion is a normal distribution. So this is the sampling distribution of the proportion, so P hat, and the middle is the population proportion P. So remember, this distribution represents all the possible sample proportions and how much they can vary just due to random sampling error. Notice that most of the sample proportions will be close and centered about the true proportion. That's why we say the sample proportion P hat is a good estimator because it is consistent and unbiased. We know that this is a normal distribution, and according to the empirical rule, 95% of the values here are within 2 standard deviations of the mean, right? Within 2 standard deviations of the mean. Remember that when we're working with sampling distributions, standard deviation is referred to as a standard error. So here, this on the left side is 2 standard errors less than P hat. So that means it would be, less than the assumed value of P, my mistake. So that would be P minus 2 standard errors. And over here, we would have the 2 standard errors above the population proportion. And so that would be P plus 2 standard errors. So that's the middle 95% of the sampling distribution of the proportion theoretically. So if we define the middle 95%, or we stick to the middle 95% as being the values that are likely to occur under our assumption, then the remaining 5%, which is divided equally into the 2 tails, so that we have 2.5% in each tail, that represents the unlikely values. So here we have 2.5%, and this is what we define as unlikely to happen due to random sampling error. And so this is the bottom 2.5%, but we also have the top 2.5% that is unlikely to have occurred due to random sampling error. So we have to make an assumption for P in order to know what the distribution actually looks like as far as filling in the numbers. And that is where the null hypothesis comes in. Remember I said since we're making a claim that is comparing to 20%, we're going to then just assume the null hypothesis is actually equal to 20%. So here, this sample proportion P, we're going to assume equals the 20%. So we are assuming that P equals 0.20. That is our assumption. So under that assumption then, the likely values will be within 2 standard errors of this 0.20. So let's see, what is the standard error for this problem? Let's go ahead and compute that. So you might recall the standard error is the square root of P times 1 minus P divided by sample size n. When we were working with confidence intervals, we of course did not know P, and we found an approximation of the standard error using P hat. Here, however, we are making an assumption about P, so we treat this computation as if P were known and P was equal to 0.2. So our standard error then would be computed as the square root of 0.2 times parenthesis 1 minus 0.2 close parenthesis divided by the sample size of 785. So that gives us a standard error of 0.0143 if we just round it down to make it a little easier to talk about. So here is our standard error for the sampling distribution of the proportion for a sample size of 785 and a population proportion of 0.2. So these values then, P minus 2 SE and P plus 2 SE, these could actually be computed if we wanted to know those actual values. Let's go ahead and do that to understand what is happening, although that is not what you would do if you were actually conducting a hypothesis test. But let's give it a shot here. So P is 0.2, and we are going to subtract 2 standard errors. Over here, P is 0.2, and we are going to add 2 standard errors. So it looks like anything between 17% and 23%, those would be considered likely if we define the middle 95% as likely values, those that would likely occur, 95% chance that anything in here that will occur when you take a sample of size 785 and in actuality the population proportion is 0.2. Notice that our p hat, which we saw was less than 0.2 to begin with, 18%, does indeed fall within the 0.17 and the 0.23, right? Our computed p hat is about, not exactly, but we know it's going to be over here on the left side, right? It's going to be here on the left side. That was why we talked about an alternative hypothesis of less than. Right, an alternative hypothesis of less than. When our alternative hypothesis is a less than, that means we're looking at the left tail, so this is referred to as a left-tailed test. Now, the probability of our actually rejecting the null hypothesis is equal to the probability of our value being unlikely under the given assumptions. So our unlikely percentage is the bottom 2.5% in the left tail. This unlikely value here is what we call the significance level. So significance level defines unlikely, and it is denoted with the Greek letter alpha. So I'll often just write it out as alpha, but let me show you what that letter looks like. So I know this is all messy, but when it gets out of the way, you'll see the alpha. Here it is. Some people say it looks kind of like a fish. All right, or you could think of it as a little a. To me, it looks like a little a. So this little a is alpha, and that denotes the probability of actually rejecting this null hypothesis because this defines unlikely. If something unlikely has occurred, well, by definition, that means it was more likely our assumption was wrong. So we will only reject this null hypothesis and support the alternative hypothesis if our value falls down here in the bottom 2.5% of the sampling distribution under the assumption that P is 20% and we're working with sample sizes of 785. So this then would be our significance level, or alpha. So that is our alpha for this problem. And for the problems we're going to be doing mostly in this class, we're going to assume alpha is 0.025. The most commonly used alpha is 0.05. As you can see, 100% minus 95% is 5%. But since I'm dividing it equally into the two tails, and I want to get a test, the results of a test that matches with the confidence interval, I am going to stick with 2.5% when we're doing either a left-tailed or a right-tailed test. So alpha is 0.025. We only reject the null hypothesis if our p-value is unlikely. So that means we only reject the null hypothesis if it's in the bottom 2.5%. So the probability of rejecting the null hypothesis when it is true, okay, is equal to this alpha, which in our case is 0.025. All right, this is the probability of rejecting the null hypothesis when it's true. It's a probability of rejecting when it's true because, remember, this is assuming the null hypothesis is 0.2. We're assuming this is the true value. If under this assumption we happen to get an unusual value just because we got an unusual sample, we would end up rejecting this, unbeknownst to us, true value of 20%. So the probability of rejecting the true value, the probability of rejecting the null hypothesis when it is true is alpha, equal to 0.025. This is actually referred to as a type 1 error. That's a type 1 error. Okay, so let's again look at what we have so far. We have a sample data, a set of sample data consisting of 785 randomly selected subjects who completed 4 years of college, and 144 of those subjects are smokers. We see that 144 out of 785 is 18% of the sample. So we're going to use inferential statistics then to see if the true proportion actually is closer to 18%, which means it is statistically significantly less than the 20%, rather than just being equal to 20%. So I assume the null hypothesis is our assumption. I assume that the true population proportion is 0.2, so that goes here. We know the distribution of sample proportions is normally distributed with a standard error equal to the square root of p times 1 minus p over n. Since our p was 0.2 and our n is 785, when we computed the standard error, we got 0.013. So according to the empirical rule, the middle 95% of the data would be within the two standard errors of the true value. So we got that 95% of the data under the assumption that the true proportion is 20%, and we're looking at sample proportions that all come from sample sizes of size 785. We see that the middle 95% is in between 0.17 or 17% and 0.23 or 23%. The 18 falls in this likely region. Therefore, we cannot reject the null hypothesis. Instead, we support the null hypothesis. And you often hear the conclusion written as we fail to reject the null hypothesis we fail to reject the null hypothesis that p equals 0.2. That means it is likely and possible that the true population proportion of college graduates who are smokers is 20%. Just because our sample got 18%, that's not enough evidence to claim that the proportion of smokers is less than the 20%, because that could have occurred just from random sampling error, right? That could just be due to random sampling error. This then is an outline. It's not all formal, not all the steps and notation are present, but this is an outline of how a hypothesis test for a proportion works. Now let me go through the steps of a hypothesis test. So first thing is we are going to state a claim. And the best tests are if the claim is a less than or greater than, but the claim could be equals to. In this class, in this section, in my videos, we're going to make claims of strict inequalities less than or greater than. The null hypothesis then will always be a statement of equality that the parameter equals whatever it's being compared to in the claim. So for us, that was that the proportion equals 20%. Now notice the null hypothesis is denoted as H sub 0 or just H0. Okay, so usually I will use H0 instead of writing out null hypothesis. The alternative hypothesis then will be the claim if you used an inequality. So H1 will be the claim in our case because it was a less than. So the alternative hypothesis we are denoting with H1, although some courses denote it as HA, we will call it H1. So this always has to be some form of inequality. So for us, it will be a less than or a greater than, but if we wanted to form a null hypothesis that was equal to the claim, so that our claim was a null hypothesis of equals, the alternative would have to be the opposite of that, which is just not equals. So if we claim a less than, as we did in our test, it's left-tailed because we saw that we're seeing if our value falls in the bottom 2.5% of the distribution. If it is a greater than, it would be right-tailed because it would be on the other side. But if it's not equals to, well, you're not equal to something if you're either too small or too big, so then it becomes a two-tailed test. We choose our significance level alpha because this defines unlikely. All right, this is how we determine whether our null or alternative hypothesis is more likely true. So it is a complement of the confidence level. And since we usually talk about the middle 95% of the sampling distribution of proportions as being the likely values, then when we do one-tailed, either left or right hypothesis tests, then we are going to use 0.025 to define our unlikely. And that's what I'm saying down here. So for a one-tailed test, alpha will be 0.025. Now, you could have something less than 0.05. I mean, obviously we're using 0.025, but it could even be something less like 0.01 or 0.001, depending on what exactly it is you're testing and how strict you have to be. You don't want to make mistakes. If you want that probability of a type 1 error to be really, really, really low, well, then you pick a really, really small alpha. After we have decided what our alpha is, but for us, we already know it's 0.025. We compute our sample statistic, the p-hat, if you haven't already done so, and the standard error. And sometimes there might be other things we need to compute. And then what we are going to do in order to determine whether it actually fell in that unlikely area, we are going to compute a p-value or probability value. Oh, what is that? Well, let's go back to our example and let's go back to our curve. All right, so we had the normal curve, middle 95%, bottom 2.5%. All right, and we saw that our sample proportion fell in the middle 95. Instead of computing this cutoff value here, which would be called a critical value, what we instead are going to do is find what's called a p-value, where the p-value is going to be the area in the tail as defined by the test statistic. Now notice, since our test statistic was in the likely region, we already determined that, we would get an area bigger than the 2.5%. If we had gotten a sample statistic that was in this unlikely area, we would have gotten a p-value of less than 2.5%, right? So for example, if we had gotten a value down here, the p-value would be this, which is less than 2.5%. So if we go back to our steps, we get a decision rule here. We compute the p-value and then we compare it to alpha. And if the p-value is less than alpha, that means it was unlikely to have occurred under the given assumptions. So we have to reject the given assumptions, which is the null hypothesis, and support the alternative hypothesis, which will usually be our claim. If, however, our p-value is greater than alpha, as in our example, we will fail to reject the null hypothesis. So formally, we say fail to reject, but for many students, it's easier to just think, well, we're not supporting the alternative, so we must be supporting the null. The important thing is to realize that in statistics, you are never actually proving anything, because we're working with probabilities. Our conclusion would then just be a sentence based on whether we supported the claim or not. And we can say the sample data supports the claim. And if you were turning in this for someone to read, like a report or a project for a boss, you would actually write out the whole sentence. The sample data support the claim that the proportion of college graduates who are smokers is less than 20%, or in our case, the sample data do not support the claim that the proportion of college graduates who are smokers is less than 20%. So that is then an outline, conceptual outline with some details in it of a hypothesis test for one proportion. In the second part of this video, or in the second video, the next part video, I am going to actually go through the formal steps that you would do if you were to turn this in as an assignment. Thanks for watching.